Sure, but oh, there we go. Okay. Thank you, Henry. Well, with that, I'm going to go ahead and get started, okay? So today's topic is Introduction to Machine Learning, which today we're actually going to cover a lot of important topics, so this is a good one. So I'm sure you guys already know machine learning is basically, exactly what it sounds like, machines that learn. It's a subset of AI, and basically you have programs or algorithms or models act without being explicitly programmed. And they basically just learn through either experience, like with reinforcement learning, or data. In most cases, it's data. So yeah, pretty self-explanatory. And there's 4 really main types of ML. But to be honest, semi-supervised learning is still like more developing because it's kind of iffy right now, but mainly we have supervised learning, unsupervised learning, and reinforcement learning. And reinforcement learning is pretty it gets pretty advanced, so we might cover it next time. We'll probably cover it eventually though, but probably next time because this one will take a long time to talk about. But today we're mostly going to be focused on supervised learning and unsupervised learning. So we have separate slides for these, so I guess we'll just move on. Or
yeah, I had a versus one.
Yeah, because we explain all of this later, so we're gonna go ahead.
Okay, so supervised learning is, like as it says, you're learning by examples, and you have labeled data sets. So you have known input and what your outputs are going to be. All of your data, already has labels on it. This is pretty accurate, and it's trustworthy because you kind of know exactly where things are going. It's like I can't remember where I heard this, but you have your supervised learning, and it gets something wrong, and then you're like, no, this is this. So then you can just kind of easily change whether something is correct or not. So if your model makes a bad prediction, that's something that you can easily fix. Whereas with unsupervised learning, your model is interpreting data and it has no kind of prior knowledge. So this is let's say I put a picture in front of you and tell you to just draw it out of nowhere. You're kind of working the same way an unsupervised learning model would, in that you just saw something, you just have the data, there's no labels or anything, and you're just making your own inferences, and you're putting out your prediction. So I show you a picture of an apple, and you don't know what an apple is, you don't know anything about apples, and then you just have to use all of the clues and try to redo that yourself. Well, a model can do that same thing, and we have algorithms like k-means clustering, which is you specify a number of parameters, and basically your data will try to cluster either by a parameter or a separate parameter, or you can have non-parameterized data where it's let's say you have blue flowers and yellow flowers, and you would try to group those things. But these are unsupervised things, where it's you can group data without having any kind of label to it. It's just picking up patterns in your data. Whereas with supervised, it's a, I guess I could say it's a more directed process. It's not it's just something that's kind of random. But there are 2 types for both of these. For supervised, there's classification and regression, and then there's clustering and association. You can go on.
All right, so real quick. So basically you can kind of think of it as, for unsupervised learning, if you just dump your kid in the pool and say, learn how to swim, and they have no idea, don't do that to your kids. It's unsupervised learning. You should probably supervise them if you dump them in the pool.
Anyway, that is quite an example.
Supervised learning is if you took your kid and dropped them off at swimming class, and you taught them how to swim with the swimming class. But that's
it's exactly what it sounds like.
Yeah. Pretty straightforward. Okay, so moving on. We have semi-supervised learning, which based on the name, you can probably figure out that it's a mix of supervised and unsupervised learning. And what they do basically is they have a small amount of labeled data. That's your supervised learn, like that's the data you would use for supervised learning, labeled data. Then you have a bunch of unlabeled data. So what you can do if you're super lazy and you don't want to hand label all your data, you can use some of these methods, semi-supervised learning. And what you do is you basically just train your model with your labeled data. And then, well, actually, because you have a model with, let's say we're trying to like predict, I don't know, housing prices or something, and you have a small bit of label data. So first you actually want to train a different model to label the rest of your data, and that's called pseudo labeling. So you take your like labeled data, you train a model to label your unlabeled data, and then you train your actual model, like your, predicting housing prices model on all of the data, the pseudo labeled and labeled. So that's pretty much semi-supervised learning. And there's something called general adversarial networks, or GANs, and these are models that use labeled data to come up with their own data, basically pseudo label stuff. And yeah, these aren't exactly the most reliable things because, we are technically making up our own data. So it's still kind of a gray area because, how can you test whether or not your data is accurate if you're making up your data? So, and there's no you can't compare it to all like current data. If you have a whole bunch of data, it's essentially you're making up data, and it's kind of a gray area right now. It's not a really good idea to trust these too much, but yeah. Joaquin, is this your slide or is this mine?
Oh, I think this one was yours, and then I was gonna do associate.
Yeah, okay, so there we go. So classification and regression are the two types of supervised learning. So with classification, it's pretty much exactly what it sounds like. It classifies data, and it works better with qualitative non-parametric data. So another way you can think of classification versus regression is what kind of data they're using. So classification, you're probably going to want to use, like an image classification. You give it an image, and the model has to say, like, is this a dog or is this a cat? And it classifies it into either dog or cat. But with regression, it's also called prediction. Like regression and prediction are pretty much, they mean the same type of supervised learning. I've heard them called both ways. So regression will use numerical data, and it's predicting like a trend through the data. So with classification, you're saying like yes or no, or red, green, yellow, qualitative data, right? And you're basically trying to label your data and trying to classify it. But with regression, you're mapping a function f, based on input x to continuous output y. So it's literally just a function. Like if you think of a linear function, like y equals mx plus b, that's one type of like trend. So like if we have, like you see this in math problems a lot. If each ticket costs like $2 and you have 3 tickets, that's $6. But if you have like 10 tickets and you have a linear line, and you can just look at the line and say, oh, 10 tickets at $2, that's $20, right? So like using that trend, you can just predict it. And of course, it'll give you numerical output because we're using numerical data. There's also multivariate regression with multiple inputs, and that also gets pretty janky sometimes, but I think we might have like a whole GA just about regression in general, because this is a pretty important part of ML. Yeah, so just remember for supervised learning, and this is with data that's already labeled, so you can classify it, like, is this a tumor or not? Or is this just like a, I don't know, like a lump of flesh? Whatever. But you can either classify data or you can predict data with supervised learning. And since the data is already labeled, if, for example, I gave the model a picture of a dog and it said, this is the cat, and I could say, no, it's not. And there's like a feedback kind of. So like, even if it guesses wrong, because the data is labeled, you can be like, no, or try again, and it can go back and redo. So it kind of learns based on the labels too. Okay, it's a pretty basic rundown. Oh yeah, this is a good image of classification versus regression. So like, if you think about green dots versus like aqua, turquoise-ish dots, you can kind of see like most of the turquoise ones are on the right side and most of the green dots are on the left side. So we can kind of see the trend here. So if I had a random dot in like the upper left corner, it'd probably be green. Or if I had a random dot in the lower right corner, it'd probably be turquoise. And that's our like divide down the middle. If you can see that, that's how we classify things. And of course you can classify with more than 2 types of like labels. So it can be like cat, dog, or fish or something. And we could have like a different way of sectioning it off. Now with regression, you see all of these data points, they follow a certain trend. So if you've seen linear regression before, which you guys probably have, then like in your calculator, a little function that's just like, find the line. Or if you're graphing things in Excel, you have a bunch of data and you have to find the linear regression line. This is pretty much it. So yeah, linear regression is probably one of the most simple forms of machine learning. But yeah, it's a good example of regression or prediction models.
Oops.
Hmm?
Hello. Okay, I'm back. Here we have association and clustering. These are 2 types, or this is how we classify unsupervised learning, which is, how we said before, is learning by observation. This is like throwing your model in the pool, without knowing how to swim. So association, the best way you can kind of think of this is like, let's say you walk into a grocery store. This is kind of how I think of it. So you're walking into the grocery store and you're going to your aisle. Let's say you ran out of milk and you have some cereal at home, okay? So you're walking down the milk aisle and you're at, I don't know, maybe like, well, actually, I'm in Austin, so we have HEB. We're very cool like that. I'm in HEB and I go get some milk and I see a coupon, and the coupon's for $2 off of some cereal, okay? So then I go to the cereal aisle and I say, ooh, that's some nice cereal, and I get the cereal. And maybe there's, I don't know, maybe there's like, $5 off of like plastic spoons. This would be something that would be handled by like an unsupervised association model. So basically, you have some non-parameterized data, and you're trying to find like frequent sets of data that like associate with each other. Okay, so like let's say you have like an item S, and you're trying to count how many times in this data set item S appears, and if it goes over blank amount, then you say this is a frequent item. And you can put these into a hierarchy, and you can classify these data. This is another way. This is hierarchical association. Basically, you can characterize the things that are in the frequent item set, and put them in order of their frequency. And basically, what you can do with this data is, let's say like a store owner. I mean, this is like a clear application of this. You can see this in like a grocery store, online, or things like that. You can use an unsupervised set without even knowing what these things are, just knowing the frequencies in the data. You can take items that have associations and find patterns between them, and you're more likely to, have like an accurate prediction. So it's like, okay, if somebody's coming into the store and they're getting milk, we can probably, squeeze a little more money out of them if we put the, coupons for cereal over here, and then they're going to go get that coupon. They're going to go get cereal. So these are the kinds of, these are things that you don't even really need to have labels on your data. The model doesn't need to know it's cereal or milk. It just sees, like you could take a log of customer purchases, and their transactions, and you could see the list of like the things they buy together. And in the list of things that they buy together, you can find these frequencies and put them, from, smallest frequencies to highest frequencies. And then you can even order those sets. So, like, let's say you have like a set, somebody comes in the store and they buy like hamburger meat, and then they buy baby diapers, and then they buy, oh, you could actually go to the next slide for this. Yeah, so I have at the top, like somebody like comes in the store, they buy bread and milk, okay? And then somebody comes in, they buy bread, diapers, beer, and eggs, and you keep seeing this set that's diapers and beer, and that could be, that's an association the model will just pick up, not knowing what those items actually are. It doesn't need to know what it is, but it can see a pattern there, okay? So then you know that people who come in and they get diapers might want beer, and people who get beer might want diapers, and we as humans can think, oh, hey, that's probably dad. He's probably like stressed out. He's going to get alcohol, but like the model doesn't need to know that. You can also see this on Amazon. Whenever you buy an item, you'll see like frequently bought items together. Like, I mean, even in your recommended page, all of these algorithms online are doing those things, and like search engines basically they actually pay for this kind of knowledge, so it's like they'll find those associations in your data and give you different recommendations. Tiffany, could you go back? Okay. So then we have clustering, and clustering is like how data is distributed. So this is more like I guess you could say like parameterized. So more things, or I guess this is like something like maybe usually like you'd have like a scatter plot maybe, and let's say like you're doing or should I use that? I don't know. Yeah, you could have like a scatter plot, and like you're doing like an experimental trial, and you could maybe be like trying to like use a model to cluster and see like what specific like experimental conditions happened whenever you were like going through each of your trials, and you could be trying to see if this model could cluster the data and like understand what happened. So basically what's happening here is you have a bunch of variables and you're reducing the dimension of your data. So like you give like, let's say like we'll use like the k-means algorithm. You're giving like k means, which it's basically find k averages in your data, and then with those like k averages, let's say you have like 3, so like you're doing like a physics experiment, and you're clustering by like I don't know, let's say like acceleration, and then you're doing like starting position, and then you're doing like maybe like jerk, which is like change in acceleration. I don't know, but like you take means of these things, and you could cluster your data on like a scatter plot, and essentially like if you have like a bunch of random points everywhere, you could take like centroids and find like an average distance and kind of like separate your data. I don't know, it's hard to explain with words. It's more like a visual thing, but yeah. Overarching theme is like you're comparing and contrasting things, and then you're reducing dimensions. You're making data look simpler when it's super complex. Both of these are kind of good, but the problem is that whenever you have a scale up in complexity, unsupervised learning models might not be super good, simply because like you like, let's say like, with the physics example, or actually, yeah, I'll just use the physics example. Let's say like, you have like 100 points. That might not be too bad. But let's say like you have like a scatter plot, and they're just like a trillion points scattered everywhere, and there's no general clustering of these points. It's going to be hard to cluster your data. There's not going to be any general trends. So most of these models tend to work on simpler data, or they come with other algorithms like accompanying them. But yeah, generally like unsupervised models, they're not as what is the word? They're not as like trustworthy as supervised. But I mean, like here you can see, like as I was talking about, like clustering, you can kind of see like a pseudo version of it. You could look at these plants, and like just like if I asked you the question, like, which of these plants has like curved leaves? This is kind of like what is it called? Like a dichotomous tree, like you use in biology. I mean, I guess. I mean, not really, but I guess. It's like, which of these has like curved leaves? And then you can already just put them into groups. You can say these ones have curved leaves, these ones don't, and there are your two groups. You would have like a K, mean of 2. You can look at the dog and the baby in the bottom and then look to your right and what is that thing? Is that a baby or is that a dog? I mean, I'm hoping you can answer, but the one on the right is a dog, and that's something we're doing with unsupervised learning, and then like as I was talking about with scatter plots, this is probably a better example than I was saying with physics, but this is like classifying states, I think, and the hardest thing with unsupervised learning is knowing your K value, so knowing how many means you'll actually need. And that, like just like how I was saying, it gets especially difficult when you have a lot of data points. So as you can see here, they're like classifying, I think it would be their centroid is like the average like distance of states or something like that. And basically you can see it's categorizing like, west states and then east states and southern states and then northern states, or, mid-northern states, I don't know, like Chicago and stuff like that. But you can see like it's grouped California and Washington and all of them and things like that. But I mean, like, without the centroids there, this would just be like a bunch of data points, I mean, it wouldn't make any sense, but you can put these on a scatter plot and then throw in your model and it all works out.
Okay, so next we're going to talk about overfitting versus underfitting, and this is a really important concept in ML. So overfitting is when your model fits the data too well, and it can't predict anything outside of your training data, because remember, if you think back to last GA, we talked about how we split data into training and testing, and then also within that training data, training and validation again. So overfitting, because we're training it on the training data, right? So if you overfit it to your training data, it means it looks exactly like this. So if your data points are here, if you overfit it, it means you go exactly from one data point to the other. And this like linear trend line is actually what we're looking for. But if you overfit the model, it'll go through exactly all of the points like that without capturing the actual trend. So if you try to test this with any other data that's not your training data, it'll be a mess. Basically, it's high variance with low bias. And what variance and bias mean? So high variance. Variance is the difference in error with your training data versus your testing data. So basically, it does very, very well on training data, and then it absolutely sucks on the testing data because it's overfit to the training data, and that's high variance because the difference in the two errors or the two predictions is pretty high. And low bias. So bias is basically like the inability for a model to capture the true relationship. So since it has low bias, it's basically not looking at the general trend, and it's not seeing the true like relationship between the data, if that makes sense. And with overfitting, typically they're overcomplicated models. And like I said before, it does super well on trained data because you overfit it to the trained data. So it won't do well on anything but the trained data. And too many leaves in classification. So leaves are, this goes with the decision trees. And actually, I think we were supposed to talk about that next week. But like Joaquin was talking about earlier, like the dichotomous key, if you think about like, he just do it in like science all the time, like, does it have like round petals or like, sharp petals or something like that? So this is just a basic rundown of decision trees, and we'll get into this later because it's also a pretty like interesting model. But basically you just ask a bunch of questions like, yes, no, is this like yellow or not? And if it's yellow, then you go down like to one branch of it, and then from then you keep asking questions. So if it has too many leaves in the classifications, it means it's asking too many questions and it can't generalize. So I guess with dichotomous keys, they have too many leaves and they're overfitting to their training data, because think about it, if when you did them in science class, like, I don't know, if we're classifying like lizards or something, then you eventually get down to one singular lizard, right? Or like one species. But if we're trying with something like predicting housing price models, so predicting housing prices models is apparently the example I use all the time, but you can't get down to like the exact price for a house. You can get down to like, well, I mean, technically you could, but what I mean is if I gave you a new house, like a completely different house that you don't know of, and you asked all the same questions, you would try to fit that house into something from your training data. So basically that new house won't have an accurate measurement because you're trying to force it into the training data set, if that makes sense. Basically, it's going to suck if you overfit, and it won't perform well on the testing set at all. So yeah, if we look at this again, basically it just goes through every single point in the data set and ignores the overall trend. Okay, and now for underfitting, which is pretty much the exact opposite of overfitting, and it's when the model can't grasp the trend, doesn't fit at all. So with underfitting, like, if we imagine like a scatter plot, and oh, I probably should bring out like MS Paint for this and pull a Henry. Okay, hold on. Wait, okay. I am sharing just this Chrome tab, so let me just share my screen overall. Okay, can you guys see like the MS Paint thing? Hopefully.
Yeah.
Yes. Okay, cool. So if you have your like graph, and then let's say we have like a bunch of data points, and this is like a quadratic function. So like you want their overall trend line to be like, I'm sorry if you can't really see the little points because they're kind of small. You want the overall trend to look like that, right? But for underfitting, if you underfit that data, you'll probably just do like that or something, if that makes sense. Or like, essentially it just misses the overall trend. So like if overfitting, can I make this size? Aha. So with overfitting, if you like, this trend is like linear or something, overfitting will make it go through like this, like we saw earlier. And I'm sorry, imagine those are going through the points because I can't draw properly with a trackpad. But if it was underfitting, it'd probably do something like this, like, nah. Actually, that's kind of accurate because it is a linear one, but okay. If it was underfitting, maybe you'd do something like that. That makes more sense. Basically, it's way off. So yeah, and again, this has low variance and high bias, which means low variance, remember, it's how they perform on the test and the training set. And if it has low variance, basically it means it sucks with both sets. And high bias is also like, so it's consistent in how much it sucks, if that makes sense. Okay, and if we're going back to the decision trees example, the dichotomous key, if you guys remember those from science class, I really did not like doing those, but it basically means it doesn't have enough leaves. So if I had like a bunch of lizards and I said, is this green or brown? That's it. And that's all I asked. And I just put the lizards in green or brown. And that does absolutely nothing for predicting the species of, I mean, it does a tiny bit, but it doesn't really do much for predicting the species of a lizard, right? Because all you know is it's green or brown. So that's what I mean by not enough leaves. It means you don't like ask enough questions, kind of. Like the branches don't split off enough. So for looking at this picture and your model performs well on your test set, then it's a good model, most likely. But if it doesn't, then we have to look at how well it performed on the training set. And if it did, if it performed well on the training set and sucked on the test set, then it was overfitting. But if it sucked on both of them, then it was underfitting. Pretty much it. So Okay, yeah, this is a better example of underfitting because you see how the trend is more like this U shape, but it's underfitting and it just says, nope, nope, we're just gonna do this linear trend line and call it a day. So, but what we actually want is this like general trend line. And if you're overfitting, you're kind of like trying to go through each one of these individually. Because these are your data sets, data points from your training set. And you want it to perform well on training and testing, if that makes sense. So yeah, underfitting and overfitting is a pretty big thing in ML. And it's kind of hard to tell if you don't like actually plot it out. So, oh, actually, I will talk about that in a second because we also have the classification. So really the trend you can see here is like this, like all our yellow circles are in this like upper right corner. And yeah, that's a pretty good like, approximation of like red, like X or circle. Underfitting is you just kind of, call it a day. You just come up with something and you call it a day and it like barely fits. Barely. And overfitting is, if you can see here, how they do it like that and they loop around those X's like that, that's overfitting. Because if you try to do that with your your testing data, and say you had like a yellow circle right where that X is, this green X, I think you guys can see my mouse, right? If you had a yellow circle right around there, it would probably say it was a green X instead of a yellow circle. So, yep. Oh yeah, so how do you know if your model is overfitting or underfitting without graphing it? We're gonna have to look at the error in the model. So if it's underfitting, it pretty much just has like high, super high error. I mean, they both start with high error, the lower your model complexity is. But you wanna find that sweet spot in where you see how like it curves over here. You wanna find that like lower part of that curve. So what you're trying to do is you're trying to find the right amount of complexity for your model. You don't want your model to be too simple because that's going to underfit, or you don't want it to be way too complex because it's going to overfit, right? So you can graph the error versus the complexity, and you can just kind of like see you want that low point over here. So yeah, and again, these are like high bias, low variance for underfitting and low bias and high variance for overfitting. Because the model performs pretty much the same if it's super low complexity, whether or not you're underfitting, under or overfitting to the data. It's pretty high error, pretty low complexity, you're not going to do pretty well. But if you're super high complexity, and the higher complexity, like you reach a certain point in which the complexity gets too high and you're overcomplicating things, and then your model just can't predict things accurately anymore. So yeah, you want to find that spot right before you start overcomplicating things, if that makes sense. If you're looking at your error, when does your error start to increase rather than decrease? If you're upping the complexity of your model, you have to check your error. And we're going to talk about evaluating your models, I think in the next slide, sometime soon. But you want to continuously check your error. And if your error is super high, probably consider upping the complexity of the model until it gets down to like until it gets to the point where it's pretty low, right? But you always want, less error, of course. So you're probably going to keep upping the complexity. And if the complexity starts going up and the error also starts going up, that's when you know it's time to stop and go back a little bit. So yeah, evaluating models. So we evaluate our models with our validation data. And if you remember from last time, there's validation and testing data, and both of which are pretty similar, honestly, because validation, after you train your model, you're going to validate it real fast. And then after you validate it, then we're going to test. So it's kind of like think of it like a test run. So how we evaluate models, and, I talked about earlier, error and accuracy. If you have supervised if you're doing supervised learning with all labeled data, then you can just look at accuracy, you know, like, is this a dog or a cat? And we can see how many of it predicted right with the validation data. So we train it with the train data, then we validate it with our validation data. So let's say with our validation data, we had like, I don't know, 10 points, and 7 of them were correct, like it was either the correct dog or cat label, and 3 of them were incorrect. Then your accuracy would be 70%. So yeah, and then we also have percent accuracy, which is, I mean, kind of similar to what I just said. Like if you get 7 out of 10 right, that's 70%. But if you're thinking about a prediction or a like regression type model, then you can see how accurate it is off of the real data set. Because to be honest, a perfect score is impossible for machine learning, because if you're thinking about that data set, like regression wise, that linear trend, it's still just a trend, and it's not going to give you the exact data point. Like that, maybe the testing point is like slightly above or below the line. The point of that trend is to get the general idea. So you're not trying to predict, you know, every house price down to the dollar, because you're not gonna, it's pretty much impossible to predict with 100% accuracy. Because remember, what we're doing is predicting. Well, at least with prediction / regression, we're predicting, we're making an educated guess. And, you know, if you get it pretty close most of the time, that's pretty good. You're just trying to look at that general trend. Okay, so we're gonna look at our error, right? So there's 2 ways we can do this. We can do the mean absolute error, the MAE, and it's exactly what it sounds like. I think you guys might be familiar with this too from like lab and stuff. So you take the absolute value of each prediction difference and then the average. So let me pull up MSP. So remember our graph, and we have a bunch of data points like that. Actually, I should make them more like linear-ish. We have our general trend that goes through like this. So we need to find the mean absolute error. So the difference between the actual point and the line, right? So like the distance from here to here, here to here, that's a big difference. Or like here to here with each of the points. And we take the absolute value because like, oops, that's kind of a bad line, but you get what I mean. So the absolute value, we take the absolute value because if it's under or over, it doesn't matter. We just want to see how far off it was. And also the negatives could also cancel the positive if we don't take the absolute value. So that's the reason we take the absolute value. So yeah, you just take the distance from your general trend line, your prediction from the actual data points, and take the absolute value of all of those, then take the average, the mean. So yeah, and if you remember from last time too, we talked about important Python libraries that we're probably going to need. So sklearn.metrics, and then you can import a mean absolute error calculator, and you just, you know, use it as a function. You shove in your little data set and you say, what's my mean absolute error? And you just spit out the answer for you. Pretty good. So another way you can do it is the mean squared error, so MSE, and it's pretty similar. You just square all the errors and take the mean, and we're squaring all the errors again because we don't want that negative or positive. We just want, you know, the difference, or like the distance between the line. So yeah, for evaluating models, you need to look at the accuracy, how well they performed on your testing data and your validation data, and you also want to look at the error. There's also validation and cross-validation, which are, they're pretty like, cross-validation is getting into some kind of like advanced stuff, but we could probably talk about it next time too. And validation again is just, you know, validating your model with your validation data. You're looking at your error, accuracy, all that kind of stuff. So yeah, just remember that a perfect score is pretty impossible. Like, it's why most models, you know, they say like, oh, it can predict whether you have cancer, like, you know, 90 something % of the time. But I mean, maybe one day we can get models that predict to 100%, but it's just kind of the nature of the game, you know? because you are predicting things. So there's always going to be some sort of like outlier or something that you can't completely predict. Joaquin.
Why is my mic? Oh my God. The muting feature. Okay. Train, bro. Okay, whenever you wanna improve your model, how do you improve your model? Well, you've gone through your first step. You train your data, you validate your data, then you test your data with the weird set off train data, and then you repeat. You can improve your data by adding more data. This is always the easiest and best way to improve your data is to add more data. I mean, it's not always the best and easy, but it's a no-brainer. You add more data. Just add more data, and the data will tell you what is wrong and what is right, and then you can continue validating and so on and so forth. Last time we talked about imputation, so let's say you trained your data, did all those things, and then you forgot that you had a couple zeros placed in there. Well, that's probably destroying your model. You should get rid of those. You don't want zeros just hanging around, especially if you're trying to make a good model. So yeah, get rid of any imputation that you have if you can. Another thing that you're going to want to do is you're going to want to treat outliers. You don't want to have like missing data or any like extreme data points. Maybe the physics example finally works now. If you were like doing your physics stuff and the freaking like, let's say you're like measuring, like you got like a photograph or something and like you're measuring speed, and like one of the times it just gets all like blurry and it's horrible, and it like goes into the like, like measurement computer thingy, and it plots your data, but it's like all whack and out of place. Well, if you're trying to make some like, linear regression or trend line of your data, you're going to probably want to get rid of that one because it's not helping you make that regression, right? So any kind of like really stupid outliers that are kind of just like, why is that there? Those things you should probably get rid of. They're not doing you any good. And getting rid of them helps improve your data. I mean, not improve your data. It does improve your data, but it overall improves your model. Then you have feature engineering, which is like transforming your data, which is like basically like, let's say I'm graphing. Actually, I could use physics again. Let's say I'm graphing and I have like my physics model and I'm doing linear regression. Well, what if I do like like a logarithmic graph and then do linear regression? What if I change like how my data is actually being interpreted, and then how and then my model will predict off of like that different interpretation. I don't know. So it's like, instead of having like, let's say your model has data points and it's like your y-axis is like velocity, and then your x-axis is time. You could have like your y-axis is like velocity squared, and then you could have time on the bottom, and then maybe you're going to get some different sort of interpretation of that data. Maybe you could be modeling something else and get some new sort of outlook on that. But yeah, feature engineering, it's just like, I mean, basically exactly what it sounds like. You're taking you're taking the data that you already have with your model, and you're just like messing with it in ways that could show you something new. Kind of like what, I guess that's what engineering does. Then you have creation. I mean, kind of like following the same principles, but it's really, like creation is just like adding in, you would derive new variables, or you could add new variables into your data maybe, and it might have higher correlations with information that is already in your model. So your model might extract a better prediction. Then you could have feature selection. So let's say you're running your model And some of the data in your set, you don't really know this, but some of the data in your set isn't actually too necessary, or it might even be harming your model. And it's not really, you don't need it there. So what you could do is you could train your data set, and you could have certain target variables and independent variables, and try to find like your best set of data, whenever you're testing. But yeah, I mean, like, this is all, I mean, like, you could be like changing, like, maybe, if you're doing like I don't know, maybe like, did we talk about a naive Bayes?
I think we like briefly mentioned it, but we never actually like explained it.
Okay, well, I'm not sure if I can do it justice in like my small, but I'll try. Naive Bayes is basically like a probability kind of thing. So like, I guess like one way you can think about it is like weather. Um, it's a type of model you would train. Correct me if I'm wrong, but it's like a type of model you would train. It's like, let's say you have like data, and you're trying to figure out like um, a weather prediction. So it's like, is it going to be? You're trying to figure out if it rains today. So it's like, okay, is it cold or is it hot? Is it drizzling or is it misty? And based on these things, it's like a conditional probability, as opposed to just a probability. So it's like, you could have, what's the probability the dog barks across the street is blank. Okay, then there's what's the probability the dog barks across the street if there's a person walking by. That could be 100. So that's kind of like what Bayes is. Bayes' theorem is. It's like it's a theorem of, it basically says like probabilities will change if conditions vary, or conditions are more favorable. I don't know. I can't remember the specific wording, but I hope you get the gist. But anyways, aside from my sidetrack, you could have like something like naive Bayes, where basically your model is doing that sort of thing. It's taking those probabilities, and let's say, you have something like that, and one of your questions is like, okay, you're trying to get to like whether it rains outside, and it's like you ask the question about dogs, let's say. So it's like you're trying to figure out if it rains outside, and you're asking like, did the neighbor's dog bark? Is that really necessary to find that out? So that's like feature selection. You could kind of like you could select important classes of data. So let's say like that class is like, like a social class or something, I don't know. And then you could have like a geography class, so you could test for things in geography class, which is like where you're situated on Earth. Does that play into whether it rains? Or, like selecting whether is that important, or is social class important? Is your neighbor living next to you important to whether it rains? Not really. So the social class would get cut out. That's something that in feature selection, if you test that class and you find it doesn't really, it doesn't improve the correlation of your model, whereas the geography class definitely does, cut out the social class and use the geography class more, expand on that. But yeah, I mean, these are just different ways that you can improve your model and improve training. I included a picture, kind of like how Tiffany had. So basically you can see like, as model complexity increases, your validation error might increase because, as she was saying beforehand, you can end up overfitting. So training your data in different ways can help decrease that validation error, because you're improving, or not improving, but you're adding new things that your data can use to improve. I mean, not data. You're adding new things that your model can use to improve through data, through engineering, and through like, I guess, trimming off like excess stuff that's not really helping it, Yeah.
Yeah, and actually, I like this picture. God, I can't speak. I like this picture better for explaining overfitting and underfitting, because it labels like that high bias and the high variance. So the variance is like the difference between the two errors, and the bias is, how accurate, like how actually accurate it is to the data, or like how faithful it is to the general trend. So yeah, this is actually, I like this one better because it labels the high bias and the high variance. And also for the naive Bayes, to my understanding, like you got the general gist of it too. Um, so all of your features are like independent of each other, and it has like a certain probability. So like if this like animal is, I don't know, actually I'm trying to think of like defining features between dogs and cats, and now I'm trying to think of like, there's not that many. So let's do like let's do something else. Let's do like okay, we can go back to the weather one. So like the probability, like if it's super humid, then it's probably more likely to rain. And forgive me, I'm not a meteorologist and I don't actually know. I've deleted all the weather knowledge from my mind. Or like, okay, so what I'm trying to get at is every feature, like every question you're asking, like what Joaquin was talking about, we consider those independently. And for example, if it's highly probable that it'll rain because of the humidity or like the dew point or something, then we'll increase the probability of rain. And if another feature is also like, yes, like it's cold outside and that also happens to increase the probability, we're just going to increase the overall probability more. So each one of those independent features, you kind of say like, is it, cold or hot, or is it cloudy or, clear skies? And then you consider each of those independently and how they contribute to the overall, like, is it raining kind of thing. And so if it's low chance of it raining or lower chance of it raining when it's hot and higher when it's cold, then we have like that overall probability, and we just kind of add all the probabilities of each of the independent features, if that makes sense. Sorry, I'm not doing this one justice either. Okay, but yeah, that's all I really have to add. Oh, and with the training improving models, yeah, like pretty much what you can do is just train it more, like practice, practice, practice. It applies for throwing your child in the pool too. You throw them in,
Okay.
throw them in there long enough.
Please
They'll
don't do
learn how
that.
to do. I mean, they'll do it better if you do it more, right?
I don't support this. I don't know.
Okay, but yeah, I think that's all we have for today. If you guys have any questions, feel free to ask. And yeah, Joaquin, you have anything to add?
Ask questions, please. I get lonely. Anybody? Alrighty.
Okay.
Well, if no questions, I wish you all a good night.
Yeah, okay. That's all we have for today. Thank you guys for coming. Glad you guys liked it. Okay.
Nice.